elements are very important things. Of all the mixtures and compounds in the whole world, they can all be broken down into elements, and the elements cannot be broken down any further. And the reverse is true as well. All the elements we have are combined to make all the different compounds in the whole world. So elements are truly the building blocks of the entire world. Elements are so important that we list them in a table called the periodic table of the elements. Looks like this. Now the table lists all the elements we know, and one of the interesting properties to start off with is that there are a total of 92 natural elements. Stepping back for a minute, this is a rather stunning thing when you think about the millions of compounds in the world, all made from combinations of just 92 different natural elements. There's also a series of man-made elements, and there are experiments to make even more, and so the total number has gone from 92 up to 118 so far with the man-made elements. Now all the elements have a name, and they're all listed in boxes in the table here. Some of these you're familiar with. For example, in the middle here is gold. Gold is interesting because it's in the minority of elements. It's a fairly small group of elements where it's actually pure in nature. It's not found in a compound. Almost all other elements are found in a compound. Another familiar one is sodium over here. Sodium is more typical. We usually hear of it in a compound such as sodium chloride, common table salt, sodium mixed with chlorine in a compound, or maybe sodium bicarbonate. Now, the periodic table also has the property that it organizes all the elements, and it's such a good tool for seeing the properties of different elements based on the organization that we always keep this around. And for any test you have in this course, you will be given a periodic table just like this one so that you can use it to help you remember how the elements are organized. Now the other thing about elements is they all have symbols, and the symbols are listed here. Some of the symbols are abbreviations of the name of the element. For example, nitrogen here has the symbol N, which is just the first letter in nitrogen. But that's not always the case. There are a lot of elements that have symbols that are not abbreviations of the word. For example, sodium over here has the symbol Na. Well, Na is an abbreviation, but it's for natrium, the old Latin name for that element. The modern English name was adopted, yet the old symbol for the Latin name is what was kept as the symbol. One thing that I should tell you right off is, since you'll always have a periodic table like this around, there's also one in your handouts. You do not need to memorize symbols and names of elements. You will tend to memorize them just by chance anyway, but you don't have to do that as an exercise. Now the periodic table organizes elements according to their various properties, and I'd like you to start knowing these things. And by elements, in this case, what I'm referring to are the not elements in compounds, but elements as pure substances. Okay, and to start off, let's look at the organization of elements into metals and nonmetals. I have a chart back here. It's color coded, and what I'd like to bring to your attention first of all is a line that I've drawn between boron and aluminum, BNaL, and then I've continued the line down, over and down, and then over and down like a stair step all the way to the end of the table. You need to write this in your periodic table that you have in your notes so you can start remembering properties of elements. Everything to the left side of the stair step is going to be called a metal, and it'll have certain metal properties. Everything to the right side is going to be called a nonmetal, and it will have certain nonmetal properties. And we can look at these. A classic metal in our lives is like the blade of this knife. It's made out of steel, but steel is mainly the element iron, Fe right there. But we expect all metals in the periodic table to share common properties with iron. For example, all metals are expected to be shiny. Most are actually solid too, but one of them is not. All metals can be, with pressure applied, smushed into flattened or smushed out shapes. We call that malleability. So all metals are malleable. They can be rolled into flat sheets, or they can be drawn into wires without breaking. Expect metals all the time, like this knife blade or this copper wire, to be good electrical conductors. I have here a light bulb. I can turn it on and it won't light because it's missing electric current between these two wires to complete its electrical circuit. But if I touch the wires to the metal, it'll light up. So there's electrical conductivity. It's a property we'll see for all different metals, including this copper. Now I'll turn this off. All metals as well will be good thermal conductors. For example, I can take a piece of ice and put it on this nice heavy block of steel, nice metal, and even while you're sitting here, you probably can see that the ice cube is getting smaller and smaller. The conductivity of the warmth from the steel into the ice is a property we expect. We expect that the conductivity will be good for all different metals. So let's switch over to the nonmetal side. Nonmetals are called nonmetals because they have the properties of metals, but the select ones they don't have. We'll use as an example this nice lump of Illinois coal. It's a almost pure carbon. It's got several impurities in it, but it will represent our nonmetal. Okay. Unlike the shiny metal, we expect nonmetals, generally speaking, to be dull. Unlike the malleable metals, we expect the nonmetals to be brittle. And if I take off a hunk of this coal and smash it in my fingers, it will break into a lot of pieces, into powder. So it's because it's so brittle. We expect nonmetals to conduct electricity poorly. They are electrical insulators. So I can turn this on and I can touch the coal, no electricity. I should stop while I'm doing this and make mention that carbon in particular has a form called graphite that actually is a very good conductor, and it's a worthwhile thing to remember. Okay? And then I can do the ice cube trick where I put the ice cube on top of the coal, and it is not a good heat conductor. It's a heat insulator, and the ice cube will tend to not melt well at all, whereas here it is completely gone. Now the other thing about nonmetals that I should point out to you is that there's one that's over here in the top of the periodic table, hydrogen, that looks like it should be where the metals are, but hydrogen always behaves like a nonmetal, so don't get confused by hydrogen being over there. The other thing about metals and nonmetals is that if you get to the elements right on the stair-step border, some of them don't quite know whether they want to be metals or nonmetals. We'll call those metalloids or semimetals. We have boron, silicon, germanium, arsenic, antimony, and tellurium. And the only one I care for you to know about is silicon, because it's a pretty important metalloid in our life. I have a bottle here it is, with silicon, and if you can see inside the bottle, it's fairly shiny. So like a metal, it's sort of got a shiny surface. But then it's also like a nonmetal because it's not malleable, and it's very brittle and it'll crumble. That's why it's in all these little jagged pieces. So silicon kind of doesn't know whether it wants to be a metal or a nonmetal. One of the really interesting properties of silicon is it's a semiconductor. It won't conduct electricity, but if you increase the voltage enough, it will conduct electricity. And this property has been used for making electrical switches for logic circuits in computers. And of course, this has been developing over half a century, and these days we have very powerful computers, all based on the switches made by the semiconductors, the computer chips made with the semiconductor silicon. This behavior is so important to the computer industry that an entire region of California that is dedicated to the manufacture of computers is named Silicon Valley.